It is 20 past 2 in the morning and you are standing 8 meters from a river of liquid iron. It came out of the furnace 4 minutes ago at about 1500 degrees Celsius, and it is running down an open channel in the floor in front of you, throwing light so bright that the far wall of the building has disappeared. The air on your face reads somewhere around 45 degrees. That is uncomfortable. It is not what would kill you. What would kill you is coming off that stream in a straight line. It does not care how hot the air is, and the only thing standing between it and you is a thin layer of aluminium bonded to a sheet of woven glass fiber. You are wearing a mirror, and in a minute you are going to walk closer. Most people assume that working next to molten metal is a problem of burns. It is not, mostly. The burn is the accident. The everyday hazard is something slower and far more ordinary, and it is the reason a casthouse crew works to a clock instead of to a task list. Here is what makes this environment different from every other hot place you have been: in a sauna, in a boiler room, in a bakery. The heat reaches you through the air. It arrives by conduction and convection. It is measurable with a thermometer on the wall, and if the number is survivable, you are fine. Next to 1500 degrees, almost none of the heat load reaching your body comes through the air at all. It arrives as radiation, traveling in a straight line at the speed of light, and it does not warm the air on the way. A thermometer on the wall will tell you it is 45 degrees in here and be completely correct and completely useless, because the number that matters is how much radiant energy is landing on the front of your body every second, and that depends on the temperature of the surface you are facing and how far away from it you are standing. That is the whole subject of this video, and there are exactly 3 ways the heat gets you. It comes at you from the outside as radiation off the metal. It comes at you from the inside as your own body temperature climbing under a suit that will not let you cool down. And it comes at you from underneath in the form of a few drops of water that have no business being anywhere near liquid iron. 3 vectors, every piece of equipment, every rule, every part of the layout of this building exists to break one of the 3. Before we clock on, subscribe. This channel takes apart the machines and the systems that keep ordinary work survivable. And now let us start where the shift actually starts, which is nowhere near the furnace. The shift starts in a locker room at 10:30 at night, and the first thing that happens is that you put on clothes designed to be worn under other clothes. This part looks like the least important step, and it is not. Underneath everything else goes a base layer, and its job is not warmth and not protection from flame. Although the material will resist flame, its job is to move sweat off your skin and spread it out so it can evaporate. Moisture-wicking base layers are specified in cast house and foundry work specifically to reduce heat stress, and once you understand the third of the 3 vectors, you will see why the very first garment you put on is aimed at the enemy inside rather than the one in front of you. Over that goes cotton or wool, never synthetics. This is an old rule with a brutally simple reason. Natural fibers char. They blacken, they burn, they fall apart, and what is left of them stays where it is. Synthetics melt. A melted synthetic garment does not fall apart. It flows, and it flows onto skin and sticks there and keeps giving up its heat long after the source is gone. In a building where a splash of metal can arrive without warning, a fabric that chars is a fabric that can be pulled off you, and a fabric that melts is not. Then you walk out onto the floor, and the first thing you notice is that the building is not one space. It is a set of zones with different rules, and you can read them off the floor markings. There is an area you can walk through in ordinary work clothes. There is an area where you need the full stack. There is a line painted that nobody crosses during a cast. The layout is not organic. Workstation layout in molten metal operations is explicitly designed so that the worker can work at a safe distance from the metal, and where distance alone is not enough, fixed heat screens are installed to add protection. The building itself is a piece of safety equipment, and the most effective control it offers is the oldest one available, standing further away, and distance works better here than your intuition expects, which is the first thing worth understanding properly. Radiant heat obeys a rule most people half remember from school and never apply to their own body. The energy landing on you falls off with the square of the distance. Double your distance from the source, and you take 1/4 of the load. Halve it, and you take 4 times as much. There is no gradual middle ground. The difference between standing 4 meters from an open stream of iron and standing 2 meters from it is not a matter of degree. It is a factor of 4, and it happens in the 2 paces you take without thinking about it. And the source side of the equation is even less forgiving. The radiant output of a hot surface does not rise in step with its temperature. It rises with the fourth power of its absolute temperature. What that means in practice is that the difference between metal at 1,000 degrees and metal at 1,500 is not 50% more radiant load. It is more than 3 times as much. This is why a casthouse crew will talk about the metal being hot today as if it were a meaningful distinction, and why an experienced operator can tell from the color alone whether to stand where they stood last time. The color is the temperature and the temperature is the load, raised to the fourth power. So the two variables you control are how far away you stand and how long you stay there, and both of them are far more powerful than any garment. This is worth stating plainly because it inverts what most people assume about protective equipment. The suit is the last line, not the first. The first line is geometry. It is worth doing the arithmetic once because the numbers are not intuitive and the crew works by them whether they can recite them or not. Take a position 4 meters from an open runner and call the radiant load on your chest 1 unit. Step into 2 meters and it is 4 units. Step into 1 meter, which is closer than anyone should be and closer than people sometimes end up, and it is 16. You have not doubled anything. You have gone up by a factor of 16 in 3 paces, and the sensation of it arriving is almost instantaneous because radiation does not have to warm the air on the way to you. Now hold the distance still and change the metal instead. A surface at 1,000 degrees Celsius is sitting at about 1,270 Kelvin. At 1,500 degrees, it is about 1,770. That is a rise of 40% in absolute temperature, which sounds moderate, and because radiant output goes with the fourth power, it produces roughly 3.5 times the energy leaving that surface every second. The metal did not get 50% hotter in any sense your body cares about. It got 3.5 times louder. Put the two together and you have the reason nobody improvises a position on a casthouse floor. A step closer and a hotter heat combined can multiply the load on the front of a person by an order of magnitude while the thermometer on the wall does not move at all. And at 11 o'clock, the first tap of your shift is being prepared, and you go and put on the rest of it. And the garment you are about to put on does not do what almost everyone thinks it does. Ask anyone what a silver foundry suit is for, and they will say insulation. It looks like insulation. It is thick, it is layered, it goes over everything, and it is obviously designed to keep something out. So the mental model is a blanket. Heat presses against it, and the material slows the heat down. That is not how it works, and the difference matters enormously. An aluminized proximity garment is built as a flame-resistant base fabric, woven glass fiber, or a similar high-temperature textile with a thin film of aluminium bonded onto the outer surface in the better product's vacuum deposited onto it. That aluminium layer is not there to insulate. It is there to be a mirror. It reflects up to 95% of the radiant heat that strikes it, straight back out into the room. The heat never enters the material at all, which is why a garment thin enough to move in can handle a load that would cook you through a much thicker unaluminized coat. Compared with a non-aluminized garment, the aluminized version also cuts the flow of ambient heat by around half, but that is the secondary benefit. The primary function is reflection. And there is a reason it is aluminium specifically rather than any bright metal. What matters for this job is how a surface behaves in the infrared, which is where almost all of the energy coming off a 1,500-degree surface actually sits. A polished aluminium film is close to a perfect infrared mirror. It absorbs very little and throws almost everything back. The dark, textured, absorbent surface of ordinary fabric does the opposite. It takes the energy in, converts it to heat in the fibers, and then that heat has only one direction left to travel, which is inward, toward you. Two garments of identical thickness, one silver and one not, are not two grades of the same product. They are two different physical mechanisms, and only one of them refuses the energy at the surface. This is also why the condition of the surface matters far more than it looks like it should. A silver suit that has been scuffed, sooted, sprayed with slag, or simply worn dull is a worse mirror than a clean one, and a worse mirror is measurably worse protection. The maintenance of aluminized gear is not cosmetic housekeeping. A dirty suit has partially converted itself into the absorbent kind, and a mirror has a property a blanket does not. It only works on what it is facing. Turn your back on the stream in an aluminized suit and the reflective surface is now pointing at a cold wall, and the load is landing on the seams and the back panels at an angle they were never the primary design case for. Crews do not turn their backs on liquid metal, and it is not superstition. The second thing the aluminium does is more visible and more immediate. When a droplet of molten iron lands on aluminized fabric, it does not soak in, it does not stick. The surface makes it bead up and roll off. That single behavior is the difference between a splash that leaves a mark on your coat and a splash that burns through into your skin. And it is tested separately from the heat performance. Molten metal splash under one standard, radiant heat under another, and a garment has to pass both on its own merits. But here's the inversion this whole episode turns on. The suit is extremely good at the first vector, and it makes the second vector worse. It has to. To reflect radiant heat and shed molten metal, it must be a continuous sealed surface. A continuous sealed surface is also, unavoidably, a barrier to your own body losing heat. You are producing heat the entire time, walking, lifting, working, and the only ways your body has to get rid of it are convection off your skin and the evaporation of sweat. Inside a sealed reflective shell, both of those are heavily restricted. So the better the suit performs against the heat outside, the more effectively it traps the heat you generate inside. Which means the thing that most often puts a cast house worker in an ambulance is not the metal. It is their own core temperature, climbing steadily inside a garment that is working exactly as designed. And the reason that is dangerous rather than merely unpleasant is the part that safety literature keeps repeating. Continuous exposure to high radiant heat can produce heat exhaustion or heat stroke, sometimes without the worker even realizing it. There is no alarm. The metal announces itself with light and noise you can feel through the floor. Your own overheating announces itself with a headache you attribute to the shift, a dizziness you attribute to standing up too fast, a small error in judgment you do not notice at all because the faculty making the judgment is the thing that is impaired. That is the enemy inside. And once you know it is there, every other piece of what follows starts to make sense, including why the crew is wearing gear that costs real money to make a few percent lighter, and why nobody works a full shift standing in one place. So it is 11:45 and you are putting on the stack, head to toe, and every single piece exists for a specific failure. The hood goes on over a hard hat. It is the same aluminized fabric as the coat, reflecting up to 95% of radiant heat, and it covers the neck and shoulders as a continuous piece because the gap between a helmet and a collar is exactly the sort of opening a splash finds. Set into the hood is a face shield, and the shield is not clear. It carries a gold coating. Gold is used because it reflects infrared and ultraviolet while still passing enough visible light to see through. So the shield cuts the glare of a 1500-degree surface down to something your eyes can work in and simultaneously stops the invisible part of the spectrum that damages them. Looking at open molten metal through clear glass all shift is not a thing anyone does twice. The coat and trousers, or a one-piece overall, cover the torso and legs. The torso and arms take the highest radiant load in most furnace and foundry work, because that is what faces the source when you are standing at a channel, and that is where the aluminized material is least negotiable. Gloves are aluminized on the back of the hand, where the radiant load lands, and leather in the palm, where you need grip and where the hazard is contact rather than radiation. The boots are leather with a metatarsal guard over the bridge of the foot, and they are worn with spats. Spats are the piece nobody outside the industry has ever heard of, and they are worth 30 seconds. A spat is a cover that goes over the top of the boot and the bottom of the trouser leg, and its entire job is to close one specific hole, the lace opening. A droplet of liquid iron that lands on a boot rolls off. A droplet that finds the gap at the laces goes inside, and it stays inside against the top of your foot, in a leather container you cannot remove quickly. Every experienced foundry worker knows somebody with a scar on the top of one foot. The spat exists because of them. And notice what the whole stack is doing. Every piece is aimed at the first vector, radiation and splash, and every piece adds weight and adds seal and makes the second vector worse. The full set is a deliberate trade. You are accepting a higher internal heat load in exchange for reflecting the external one, and the trade only works if something else is managing the internal side. It is also worth knowing that none of this is left to the manufacturer's judgment. Each item of aluminized apparel is evaluated against separate standards for separate hazards. one test regime for molten metal splash, a different one for radiant heat, and in Europe the set is specified under its own standard for protective clothing against heat and flame. A garment does not get to pass on the strength of looking substantial. It has to survive metal being poured onto it, and it has to survive being held in front of a radiant source. And those are two different tests, because they are two different physical events, which is why the stack is a stack rather than a single garment. There is no one item that solves radiation, splash, contact, eye damage, foot penetration, and lace gap entry simultaneously, so the solution is 6 or 7 items each, optimized for one of them, assembled so that no interface between two of them leaves a gap. The interfaces are where the design attention goes: hood over collar, glove cuff under sleeve, spat over lace, trouser leg over boot. A cast house crew putting gear on in the right order is not being fussy. Each piece has to overlap the next in the correct direction because a splash running down a suit needs to hit an overlap that sheds it outward rather than a seam that funnels it in, and every one of those overlaps is another few square centimeters of sealed surface and another small increment of heat you now cannot get rid of. But first there is a rule older than any of this equipment, and it is the one that gets broken. Just after midnight there is a moment in your shift that looks like nothing. Somebody sets a tool down on the floor near a puddle, and somebody else picks it up and walks toward the channel with it, and a third person says something short and unfriendly and takes it off them. The rule is that water never goes near molten metal, not a wet tool, not a damp ladle, not a puddle on the floor in the path of a pour, not condensation on scrap, not moisture in a graphite tool, not a bottle of water set down on a ledge above a runner. And the reason is a matter of physics that leaves absolutely no margin. When water contacts molten metal, it does not warm up and boil in the ordinary sense. It flashes. It goes from liquid to steam effectively instantaneously, and steam occupies enormously more volume than the water it came from, at atmospheric pressure on the order of 1,700 times as much. A teaspoon of water becomes something close to 2 liters of gas in an instant at the point where it touched the metal. If that transition happens on an open surface, you get a violent spit. If it happens underneath the metal, under a stream, under a pour, trapped beneath liquid iron in a ladle or a mold, the expansion has nowhere to go except upward, through the metal, and it throws liquid iron out of the vessel in every direction. The industry term is a steam explosion, and it is not a metaphorical use of the word explosion. What makes it dangerous rather than merely known is the quantity involved. This is not a hazard that requires a bucket of water. Even small traces of humidity, on metal scrap, on graphite tools, on the inside of a crucible, are enough to produce unwanted projections of hot metal. A tool that has been rinsed and looks dry. A ladle lining that was patched and not fully cured. A floor that was hosed down at the end of the previous shift and has a low spot that did not drain. These are not exotic failures. They are ordinary industrial housekeeping. And in this one building, they are lethal. And here is why the moment with the tool matters more than the equipment does. Every garment in the stack is rated for splash. It will shed a droplet. It will bead metal off the surface and buy you the seconds you need to move. What no garment is rated for is being inside the volume of a steam explosion, because a steam explosion does not deliver a droplet. It delivers a spray from below at a velocity and volume that finds every opening in a suit designed for radiant heat and rolling splash. This is the vector where the PPE is not the answer and never was. The answer is that the water is not there, which is why the controls against this vector are entirely procedural and physical rather than protective. Keep the workstation laid out so people work at a distance. Install fixed heat screens where distance is not enough. Control what enters the zone. Nothing gets carried toward the metal without somebody checking it is dry. And that brings us to the thing the whole shift is actually organized around, because the second vector cannot be controlled by any of this. It is 1:30 and the crew is coming off the floor, and the tap is not finished. Nobody is hurt, nothing has gone wrong, and this is not a break in the sense of a rest. It is a scheduled removal of people from an environment, and it happens because of a problem the equipment cannot solve. The paradox is straightforward once you have both vectors in view. The garment must be a sealed, reflective surface to work at all. A sealed surface prevents your body from shedding heat. Therefore, the better the protection, the shorter the time you can safely wear it. There is no material solution to this. You cannot make an aluminized suit breathable, because a breathable surface is a surface with holes in it, and a surface with holes in it is not a mirror and does not shed splash. Every improvement to the outward performance tightens the inward constraint. So the industry resolves it with time and with layout, not with fabric. The controls are the ones you can see if you watch a cast house for an hour and know what you're looking at. Work is broken into cycles with the exposure length set against the conditions rather than the task. Crews rotate through positions so that nobody holds the closest station for a whole cast. Rest happens in a genuinely cooler space, not just a step back from the channel, because recovery requires the body to actually be able to shed heat rather than merely take on less. Fluid intake is scheduled rather than left to thirst, because by the time thirst is doing the reminding, the deficit is already established, and the base layer you put on first, hours ago, is quietly doing its part this entire time, moving sweat to where it can evaporate so that the little cooling capacity the suit allows is not wasted on saturated fabric. Fixed heat screens do something similar for the same problem from a different direction. A screen between a worker and a source does not just reduce burn risk, it reduces the radiant load the body has to deal with in the first place, which lowers the internal heat the suit then has to trap. Distance, screens, and rotation are all interventions on the second vector disguised as interventions on the first. There is one more control that does not look like a control at all, and it is the reason a new starter on a cast house crew is not put on the closest station in their first week. The human body genuinely adapts to working in heat, but slowly and physiologically rather than by getting used to it. Given repeated, progressive exposure over something in the region of 1 to 2 weeks, the body begins to sweat earlier in the shift, sweat more, and lose less salt while doing it, and the heart rate at a given workload falls. That adaptation is real and measurable, and it is also perishable. A couple of weeks off, a holiday, a spell on lighter duties, and a good part of it is gone. Which means the most vulnerable person on a hot floor is not always the newest one. It is sometimes the experienced one coming back from leave who is working to the standards he held a month ago in a body that no longer matches them. And the reason rest has to happen in a properly cooler space rather than a few paces back from the channel is that recovery is not the absence of heat gain. It is active heat loss, and active heat loss requires an environment your body can actually dump heat into. Standing at the edge of the floor in the suit, still taking a reduced radiant load, still sealed, is not recovery. It is a slower version of the same problem. The brake only counts if the gear comes off and the surroundings are genuinely cold enough for the body to run a deficit for a while. There is also a distinction worth drawing here, because it explains what these suits are not. The gear a cast house crew wears is proximity equipment. It is designed for working near an intense radiant source. It is not designed for entering flame, and the two are engineered differently. An entry suit built for total engulfment uses different materials entirely because aluminized fabric stops being useful the moment heat is being conducted directly through it rather than radiated at it. A proximity suit facing a stream of iron is doing the job it was designed for. The same suit in contact with fire is a different and much worse proposition. Nobody in this building is dressed to walk into anything. They are dressed to stand near it, briefly, and then leave. So the shift is structured as a series of brief approaches with recovery between them, and the thing being managed is not the metal, which behaves entirely predictably, but the people who do not. Which raises the question this whole video has been walking toward. If the equipment is this good and the procedures are this specific, what actually goes wrong? Let us be honest about it, because pretending this is a solved problem would be absurd, and the crew you have been standing with all night would tell you so immediately. The dramatic failure is the one everyone imagines: a splash, a spit, a steam explosion, metal where it should not be. Those happen, and when they happen, the equipment does what it was built to do: beads the metal, sheds it, buys the wearer the seconds needed to get clear. That is the honest description of what a suit provides, not immunity, seconds. The aluminized material is designed to reflect the radiant load and to shed the splash long enough for a human being to react, and everything after those seconds depends on the human being reacting. But the more common failure is not dramatic at all, and it is the one that follows directly from the second vector. Heat stress builds without a clear signal. The published guidance says it plainly. Exposure can produce heat exhaustion or heat stroke, sometimes without the worker even realizing it. The early stages are a headache, dizziness, nausea, symptoms that in a hot building at 3 in the morning are indistinguishable from being tired. And the documented consequence is not only the medical one. Heat stress degrades job performance and produces careless and costly mistakes, which in this specific environment means a person whose judgment is quietly impaired is now making decisions about where to stand relative to liquid iron and whether a tool is dry. That is the mechanism that connects the two vectors into one problem. The heat outside is managed by equipment. The heat inside is managed by procedure. And when the inside management fails, the first thing it takes away is the faculty you were relying on to follow the procedure, which is also why the failure almost never traces back to a suit not performing. It traces back to a shift that ran long, a rotation that got skipped because the cast was going badly, a rest break taken standing up at the edge of the floor instead of in the cool room, a tool that somebody was sure was dry. Every one of those is a decision made by a person under conditions specifically designed to make decisions worse. And that is where the architecture stops and something else takes over. It is coming up on 6 in the morning and the light outside has started to change. Let us close the three vectors because by now each has an answer. The heat from outside is broken by geometry first and material second, by standing further away, where the inverse square law does most of the work for free, by fixed screens where distance is not available, and by a garment that reflects up to 95% of the radiant load rather than trying to absorb it. The heat from underneath is broken entirely by control. Nothing wet enters the zone, because no equipment on Earth is rated for a steam explosion. And the heat from inside is broken by the clock, by rotation, by exposure limits, by real recovery in a cooler space, by scheduled fluids, and by a base layer doing quiet work under everything else. That is a genuinely impressive set of defenses. It also contains, at its center, a component that is not engineered. Because every one of those controls requires a person to act. Somebody has to call the rotation when the cast is running late, and the temptation is to keep the crew in position. Somebody has to take the tool off the person walking toward the channel with it. Somebody has to notice that the man on the closest station has gone quiet and is moving slightly slower than he was an hour ago, and is not going to mention it himself. Because the specific cruelty of the second vector is that it disables the person's own ability to detect it. Heat stress does not announce itself to the affected worker. It announces itself to the one standing next to him. So the last line of defense in a building full of aluminized fabric and fixed screens and painted floor markings turns out to be one worker looking at another and deciding to say something. Not the suit. The suit buys seconds. The colleague buys the shift. And when you walk back out through that locker room at 7 in the morning and take the stack off in the order you put it on, the thing you have actually been protected from all night was not the 1500 degrees. That was the visible part, the loud part, the part with its own light. The thing that was quietly trying to get you was your own body temperature in a garment built to save your life, in a building where the only reliable warning system is somebody else paying attention. If this changed how you think about a job you have driven past without ever picturing, subscribe. This channel opens up the machines and the systems that keep ordinary work survivable. Next time, 2 miles underground in a deep gold mine, where the rock face itself is 50 degrees and the machine keeping everyone alive is a refrigeration plant that is not allowed to stop. And tell me in the comments which you think does more here, the equipment or the crew watching each other.